Okay, so let's kind of start where we left off yesterday and take another quick look at these jet algorithms, and then I wanted to say a few words about like they're different ones that I briefly mentioned yesterday during the questions. Maybe I'll take the mask off. That's okay, right? Because it is a little difficult to talk for a longer time. Okay, so right, so this is what we had yesterday. Where we start with this event with this Lego plot, where you see the energy of particles and the rapidity and phi, the azimuthal and the polar angle plane, right? And then we want to basically group those particles together into jets, right? That ideally they want to connect to actual particle level quantities. So yesterday we looked at this algorithm in particular, right, where we have a distance metric, a pairwise distance, which is basically the geometric distance in that plane, and then we have divided by the jet radius that basically then acts as a cutoff, right? Whenever that quantity here is less than 1, that will not be any more one of the smaller ones, but then we have this beam distance to compare with that basically gives us the stopping criteria when we stop putting particles together. And here, specific for this anti-KT algorithm, that just means that there's 1 over the transverse momentum squared. That's basically what's sort of the characteristic feature of the anti-KT algorithm. And that basically means that a soft particle gets, so like very low transverse momentum, it has a very long distance, right? And that means if I look at my list of distances, it's going to be at the very top. And I start with, I say at the bottom, right? So it has very long distance and will be clustered last, right? So I start basically with the highly energetic particles here, and then I sort of group around them the softer ones, and the softest particle comes in last. Okay, so that's basically the reason that you find these kind of circular jets, right, where you have the hard particles in the middle, and at the end you sort of put the softest ones in, like here, right, and that's why you get these circular shapes. Maybe one comment why you actually get an actual circle, right, even though there are no particles here specifically. That's why you basically have like infinitely small energy particles everywhere to like get these circular shapes. Otherwise, of course, they don't look like a circle. Okay. And so to make again the point, there's no unique definition, right? We went through this with a different algorithm, right? Where now the transverse momentum here is in the numerator as opposed to the denominator. And that basically inverts the whole thing, right? Now when we basically start by combining softer particles already at the beginning, as opposed to putting them in at the end, right? And so we went through this entire procedure here in this example, in this one-dimensional example. We found these 3 jets. And so what I still wanted to point out is that this now looks different, right? So this was the 1D example, right? But if we go back to 2D, right, but if we actually have an experiment, right, if we unfold this cylinder, then we actually really, so this is what we started with, right? That's the anti-KT result. So this is always the same event, right? That's what we get with the anti-KT algorithm. And here are 2 other examples. And so here's what they are. So there's like an additional parameter now introduced here in this distance metric, which is this parameter P. So that's both in the pairwise distance between 2 particles and in this beam distance, right? We have here an additional exponent P. If we set P equals 1, right, then we just end up with this anti-KT algorithm, right? So that's as before. And now if we choose P equals -1, then this will go into the numerator, right? It's just KT squared. And that's the KT algorithm that we saw in this one-dimensional example that's down here. And if I set P equals 0, right, then this entire thing just disappears, right? This will be 1, this will be 1. So I still have a stopping criteria, but it doesn't depend on any momentum anymore, right? So it's going to depend on the geometric distance in this plane, right? And so in that case, that's called the Cambridge-Aachen algorithm. There's 2 groups sort of came up with this at the same time. And as you can see, I don't know how well you can see it from distance, but like, yeah, no, I hope you can kind of see it, but like these things all look different, right? Like there's different associations of the particles depending on what algorithm you choose, right? For example, let's take this one here, right? There's a cluster of particles here, right? But if you actually check down here, like it doesn't even exist, right? So with that particular algorithm, it didn't even find a jet in this region here, right? Whereas it's kind of there for this KT algorithm, but it looks definitely quite different, right? They're definitely not round anymore, and it's definitely different, set of particles that are associated with that region of phase space, right? And so that's sort of the a point that they are not unique, right?
Are the
Yeah. Right.
colors associated with anything, or were those just arbitrary? Okay.
Yeah, that's random colors. Things. Yeah. Right. Yeah. There's no. I guess they're just like numbered in a certain way. I'm not quite sure how. That's right. But if you look at like particular region of phases, it's always the same particles. But then when say like there was definitely also like a jet here, but it didn't pass, like the total momentum of that jet was not above a certain threshold, right? And then it was basically just removed from the event, right? Like right, with all these particles, right? There were some here, right? But if it's not an actual jet that we count, then that was just removed in that particular illustration. Yeah.
All of this is clustering techniques, right? Like, is there a regime where one is preferred over the other?
Yes, so that's what I'll talk about the next slide. Exactly. So they have different advantages, and this sort of depends on what you want to do. So one of the advantages, let me see if I have this here. Yes, so I have the advantages on here. So one of the advantages of the anti-KT algorithm is that they're circular. They give you like a round shape, and it turns out that that's actually really good for experimental analysis. That's why they initially started with a cone algorithm, because that always gives you an actual cone, right? But then we have these issues with either safety or they have other disadvantages. But the nice thing about this algorithm is that you get these round jets, and that turns out to be very useful if you want to do an experimental analysis, to do something like jet energy calibration, if you want to do unfolding of your measurement and things like that. Then it's very useful to sort of have a nice shape in your detector. I don't know all the details, but apparently that's like really useful. You can do much better, more precise measurements if you use that particular algorithm. So that's one of the advantages. The others have advantages too. Neither of them are round, but they have other ones. So let's, for example, look at this one. So the KT jet does not have that, but what it tries to do, it tries to mimic the actual partron branching mechanism that produced the jet. That's basically how it was initially introduced. And so the way you can think about it, I don't know if you can see this drawing here very well, but it's again sort of this idea, right? If we start with sort of two distinct directions, right? Say an initial QQ-bar pair, then there's gluon emissions. Say one here, so in total it's 4 partrons here, right? 4 particles. And so the idea of partron showers is that they're ordered, for example, in KT. So if you look at partron showers like Pythia, then that's a KT ordered shower, right? Where you basically start to order them, like any additional emission is at smaller KT than the previous one. And so the idea here is then the jet algorithm basically undoes those splittings, right? So it basically goes backward, right? So in that sense, it sort of tries to mimic a physical clustering procedure, right? Where say I start with this one in KT, right? I put this back into this one, right? That would be the first clustering step. I obtain this, and then the second step, say this is ordered in KT, right? And I combine it with this one, and I stop, right? And so the advantage here is that it has sort of this physical structure, right? Of course, that is somewhat approximate, right? Like Pythia is also not perfect, right? There's like a lot of issues with it, but it sort of mimics that structure, right? And so the advantage that may have is if I'm not just interested in saying that there's a jet with a given energy or with a given transverse momentum, but I actually want to look at the substructure of the jet, then that actually can tell me more potentially, right? Because the entire clustering history, when I know the entire clustering history, how I got the jet to begin with, and I can try to interpret that, and I can try to interpret that in terms of partron showers. And that's sort of, if I can just add that, that's sort of the second idea of jets. So one of the main points of jets is that there's this correspondence if one partron is one jet, right? I mean, up to corrections that we can hopefully calculate. And And the second is because of this history, right? Because of this algorithmic structure, it very closely resembles an actual partial shower that has sort of like a physical meaning, right? That we can hope to interpret, right? And this KT algorithm tries to follow that. And that's basically why this was initially introduced. This was the first algorithm, actually, of these sequential clustering algorithms. Sorry.
So my understanding was this clustering is a technique for machine learning. Like, it helps us group our data points better.
So here, I wouldn't know. not in this context. I mean, you can use it for machine learning,
So
but
lets us understand the physical process happening better.
yeah. So the main point why you introduce them like that is that you can compare to perturbative calculations on the theory side. And so often using, for example, this algorithm will make it easier to compare to theory calculations. That's sort of the main point. Like generally that's certainly true. Like clustering, like grouping things together is a technique you can use for machine learning and things like that, right? But that's not why these things were introduced, right? Like you can still do that, right? But the main point why you introduce all these things, right, is that later we can do perturbative calculations that I'll try to cover later
one
today.
Be exclusive of the other? If it gets hard,
Second.
so would one of the techniques imply that the physical process which is happening is exclusive? Like if the jets are circular, they did not come from Parton showers, or if they are coming from Parton showers, they are not circular.
So this is like an approximate equivalent, right? Like the event is always the same, right? It's just about how you interpret it, right? And you can do a calculation using the anti-KT algorithm, right? And you can also do a calculation using the KT algorithm. You can do a calculation, using this algorithm, or you can use a cone algorithm as long as it's infrared cone assay. You can do a calculation one way or the other, and then you can compare, right? You just have to make sure you're using the same for both, if that makes sense, right? But it's just that like some theory calculations that hopefully I'll get to are easier to be done using this type of, right? Like the jets that I find with this algorithm, I can much easier do a theory calculation for that as opposed to this one up here, because this has not a physical like clustering history, right? And so actually often people combine that. They first identify a jet like this, right? Because they're round, so you can measure them easily. And then they take all the particles you have in the jet and you just recluster them with a different algorithm to basically get a more physical clustering history. That's actually what is used here. So this is this, Cambridge-Aachen algorithm. Here, this was ordered in KT. This will be ordered in angles, or basically in distances, right? I basically start with the smallest, and then I, look at larger and larger distances, right? And so that's what is called like an angular ordered clustering history. And so that's actually what you often use for jet substructure. That you first start by identifying the jet and measure its total transverse momentum with the anti-KT algorithm, and then you go back and look all the particles that you found, say, in this jet, and only recluster those particles by themselves, and then look at the structure in terms of that new clustering history. And the reason is that it simplifies a lot of theory calculations. If you try to do the same jet substructure calculations for this algorithm here, it turns out to be not as well under control as if you do this, right? But of course, if you have like infinite computing time, right, and you can do any calculations with all orders and perturbation theory, right, then they're kind of much more equivalent, right? But it simplifies things a lot in many cases to do sort of this one-to-one comparison. But they, of course, all originate, right? It's always the same events, it all originates from the same underlying physics. Okay. But like an important point here is definitely, right, that you have a choice, right? Like there's no unique way to say, this is a jet. It always depends on the prescription you choose, and the choice of prescription depends on what you want to do. Right? If you want to compare to perturbative calculation, then you have to choose one of those that you can, that is suitable to do a calculation with. Okay. Any other questions? No. Okay. All right. Lastly, I briefly wanted to mention, just because that appears often in the literature, there's also a dependence on how you group particles together. So right, when you have your clustering, right, and you find the pair of particles that has the smallest distance, then you group them together, right? And before I sort of didn't say much about it, right? We just used what is called the E scheme, where you just sum the two form vectors together, right? So right, it'll look something like this, right, where you have like two particles and the dashed line is the sum of the two. But there are other schemes how you could add them together. For example, what you could use is this so-called winner-take-all scheme, where you just basically align the direction of the combined particle with a more energetic one. Right. That's also an option. And again, here it sort of depends on what you want to do. If you're just interested in the total jet transverse momentum, this will have a relatively small impact, as it turns out. You can basically just run the simulation twice and see, right, and you'll find it's very similar. But if you look at jet substructure, that can be very important. And for example, if you're interested in something like TMD measurements, then that turns out to be super important. Like it can really change the physics completely depending on what choice of your axis you make. And so I'm not going to go into more details, but it's kind of a thing that appears very often in literature, and it sort of can really change the physics depending on the question you're asking. Okay, so all of that so far was kind of LHC oriented, like very high energy jets, right, up to multiple TeV. And so I wanted to say a few words before we go into the perturbative QCD calculus. I want to say a few words about lower energy jets, in particular those that we'll have at the EIC. Because of course, right, like all of this was developed in the context of the LHC, and well, of course, with Jefferson Lab, right, being interested in EIC physics or being involved in that, it's of course important to think about what happens if you go to these really low energies. Can we still think about jets in a meaningful way, or are there potential issues, right? And so I'm sure you've seen those things, but just sort of the timeline of the EIC, right, and where jets came in. When I started, with this 2010 report of the INT, and then the white paper in 2015, and like there was really no jet physics in that white paper. I think the word appears maybe once or twice, but it's not.
There was something in 2010.
There was something here, I see, but at least this one I think did not contain it, right? And so, but now in the yellow report, there's actually quite a lot about jet physics in there, and so what really has changed is sort of that we understand much more about the theory of jets since then, and just to give a couple of references, some so maybe not the most recent list, but really for all aspects of the EIC science program, whether you're interested in spin physics, whether you're interested in TMDs, like the 3D imaging, if you're interested in small X physics, also hadronization studies and EA scattering with the cold nucleus. For all these things, you can basically use jets. Now, of course, they're going to be very different, right? So here's just, again, an illustration from the Atlas experiment. Not sure how well you can see that. It's maybe a little too small, where you produce kind of 10 jets, right? And there's a lot of stuff happening in the event. And what you can see here is a simulation for the EIC, where you have, again, it might be a little bit dark, but you have the beam coming in. You have a scattered lepton here, and then you produce basically maybe one jet in this opposite direction, right? And if you look at also the quantities, right? For example, the energy of the transverse momentum of these jets, right here is again some data from Atlas that starts, say it's 70 GeV and it goes up to 2 TeV at that particular plot, but I think they have jets that go up to more, even more than that. So it's really TeV scales, and at the lowest value, right, we can reach is like 70 GeV. And now if you look at the EIC, and that's really sort of the highest we can get, these are exactly those jets that we have here in the lab frame. Then this is again the cross-sectional differential in the transverse momentum. Then we start at like 5 GeV and we go up to 40 GeV. Right? So we're not even going to reach sort of the lower level of the sort of the lowest PT that we achieve at the LHC. Right? They actually have problems measuring down to much very low PT. So it's really completely different energy range, right? And so one has to ask the question: does it still make sense, right, to talk about jets here? They're going to have much fewer particles, much fewer jets in the event. And well, in both cases, you see the cross-section just drops very rapidly if you go to a higher PT, right? This is a log plot here, right? This is many orders of magnitude that this cross-section drops, and basically same over here, right? Like if we go to a higher PT, we very quickly then run out of events at the EIC. Also, the number of particles, which is shown here, that's not just number of particles from 0 to 12 as a function of the jet transverse momentum, say up to 30. So not exactly the same kinematics. And the total number of particles, including some variation, is shown here in black. So we start at 2 particles, right? And then we go up to say up to maybe 10 or maybe 12 particles at most, right? So it's not going to be that many particles per jet, and they're going to have generally low momentum. And so the question is that still, useful? Sorry, let's skip that. To think about jets. And so one way to try to visualize that is to just do like a Pythia simulation. And that's basically what is shown here in those 2 plots. Right, we have to see in that diagram several times at the school, where we have an EIS event, where we have an incoming electron that scatters off, say, a proton, or in particular scatters off a quark. And then the quark basically, continues here and will eventually produce a jet, and it will hadronize, right? And so what you can see in these 2-dimensional plots here, these kind of polar coordinates, is basically just trying to map out the kinematics at the EIC, where we're going to find the struck quark. So this is like a simulation now in Pythia. It's not a strict perturbative QCD calculator. It's more like a simulation, but it can give us sort of an indication of what to expect. And so what you can see here is in the radial coordinate is just the 3 momentum, or the absolute value of the 3 momentum of the struck quark. Right, that's something we don't really have access to in experiment, but in the simulation we do, right? And so we can sort of take it as a first estimate to sort of try to understand what's happening at these very low energies. Okay. And so on the angle here, you see basically the rapidity, right? The rapidity is basically the polar angle relative to the beam axis. Right? You can think of the beam axis basically going in this direction, and then central or mid rapidity is here. That's exactly transverse to the beam. And then you basically go forward or backward into the beam direction where the beam is here. Okay. And so here in this 2D histogram, you then see basically where you expect to find in terms of momentum and rapidity, the struck quarks in DIS processes at the EIC. Okay. And in the upper plane, or the upper half plane of this, you see the scattered electron. Okay, so that's going to be in this region here. So it's basically just mapping the kinematics of these 2 scattered particles, so the electron, the scattered electron, and the struck quark. And so ideally, right, what we want to do is we want to get access to this quark distribution here. Right? We want to understand protons, neutrons, heavy nuclei in terms of quark and gluon degrees of freedom. Right? So ideally, we want to somehow recover that quark distribution. Right? And so now, and ideally, jets, of course, should get us to this, right? And so what we can now do in the simulation is not just to recover the struck quark, but we can run the entire simulation that then eventually hadronize, right? And so what you see in the second plot here is the distribution of hadrons, again, in terms of their 3 momentum and in terms of rapidity. And so this transition basically from quarks here to hadrons, that's what happens if you run the full simulation. If you have the entire shower, right, it emits a bunch of additional gluons, say, and eventually everything hadronizes, and in the end you record the hadrons, right? And the interesting thing is, right, from this distribution here, it's really far away from the parton level distribution that we actually would like to have, right? And I mean, that's really the only thing we have access to in experiment, right? That's the hadron distribution. But we would like to, have access to partons. And so what you can do now is you can just take all those hadrons, right? Run a jet clustering algorithm. And then what you find is actually this distribution here shown in red, right? That's basically the jet. So we're using anti-KT algorithm. We measure the free momentum of all the particles, or of all the jets, and look at their rapidity. And then if you compare the red distribution to the purple distribution over here, you see that this is actually really close, right? So even at these low energies, jets are going to be really good proxies for these parton level kinematics. Okay, even though here now we're looking at almost 90 GeV of center of mass energy, and we're looking at transverse momenta between 10 and 30 GeV. So it's really much lower energies than what we would have at the LHC. But apparently also here, these jets are really good proxies for particle level kinematics, at least as far as we trust a Pythia simulation. Okay. Here, of course, then the second step will be to actually check if we do, say, a perturbative calculation, does it kind of agree, right, with a simulation, and then we can compare, say, to Hera data or Bell data and see if we can actually describe these very low energy jets as well. But as it appears from the simulation here, and that's sort of one of the, I would say, one of the main motivations is that we can actually really use jets even at low energies, and it's really doing the type of thing that we would like to have. One more thing I'd like to point out is that here we're just really recording the quartz versus here there's sort of, this is like the entire simulation, right? And you see a bunch of stuff in red here, right? That's sort of going down or close to the B pipe, right? And you see that there's really kind of a separation between that, these two regions, right? That's sort of what you would associate with a struck quartz, and this is kind of other stuff, right? And so traditionally, you refer to that as current and target fragmentation. And as you can see, they're very cleanly separated there, right? There's like almost nothing in between. And the physics of current and target fragmentation regions are very different. If you know more about DIS and JLab, that's always like a big discussion, right? But if you use jets at the EIC, like you don't really have any issues separating those two regions, versus if you use hadrons, right, it's much more difficult because these two regions are completely merged together and you need to use more sophisticated techniques to actually separate the two. If you use jets, that sort of comes kind of for free in the end, and you don't have to worry about that too much. And so the question that now brings us then to, yes?
Well, now that you cluster the jets on the right, can't you say that the hadrons that went into the jet clusters are in the current region, and the hadrons that went into the other, the thin jet, are in the target region? So you can use a jet clustering even as a classifier of hadrons in the middle plot.
So of course, it may of course include some, right, that very few, hopefully, right, that you would normally associate with a target fragmentation as opposed to the current. But like as long as the jet algorithm works correctly, it would be a very small correction. So it definitely should ideally work as something like a way to separate out these two things, right, which otherwise you would have more trouble with. And then it sort of depends on the observable, right? Like it could, of course, be that if you find a substructure observable, for example, that's very soft sensitive, that you include some hadrons that maybe you shouldn't have. It's just for the total momentum, it's not going to be an issue. But it's, of course, if you come up with a very specific observable, right, where that could potentially be an issue, right? And so that's something we'll have to check if the jet algorithm does it correctly for a specific observable. So it's definitely observable dependent, I would say. But yes, in principle, you would trust this, right? And if you're then interested, for example, in fragmentation, right, you can measure all the hadrons, right, that you find in those jets, and for example, extract fragmentation functions like in jets as opposed to in the entire event, right? That I would expect to be or hope to be more reliable in terms of the separation than if you would do it otherwise. If that makes sense, yeah.
Is that wide type elasticity or rapidity or something else?
It's elasticity, yeah. Right. Yes, right. Yeah, rapidity here is written as eta. So, but yeah, so like in rapidity, right, as pseudo rapidity and actual rapidity. Usually we don't, and one of them is eta, the other one is y. So yes, that's a little bit of potential confusion. Here, I'm using them kind of interchangeably. Usually, if they're massless, same thing. Okay, are there any other questions? Okay, so then the question we need to answer, right, is why does this actually work so well, right? Like why are jets so close to particle level kinematics? Right, we discussed this yesterday, and we've seen this now even at the EIC. So ideally we should, try to get a first principles understanding of why that actually happens, right? And so that's where basically we should, look at perturbative QC calculations to try and understand that. Okay, so before we start with these calculations, and I'll try to show a little bit how the calculations work, and then if you're interested, we can discuss a bit more. I can give you some references how to do these calculations. It's really I try to just sort of cover a couple general things, and then hopefully can look at some papers and understand how this is generally done. One important distinction one has to make for these calculations is what I already briefly mentioned yesterday, is whether you think about exclusive or inclusive jet production. And so that's what I'm trying to illustrate here. So here we had yesterday this example from these Sturman-Weinberg jets, right, where you fix basically the number of jets that you're going to find, right, before you even run your algorithm, right, you fix it to be 2 jets. And so that's right, you only count events where you have 2 jets, right? And everything else you basically throw out, right? You don't count that to your cross section. And so that's like one example of an exclusive measurement where you basically put a cut or a constraint on the out of jet radiation, right? Where you require that any like the sum of the total out of jet radiation is below a certain cutoff. That's something that's most conveniently done in the plus or minus collisions, right? Because like you don't have these incoming protons. Right, if you have incoming protons, they will emit a lot of radiation, also just very collinear to the beam direction, right? And if you then, sort of depends on until where can you actually measure that, right? It depends sort of on the rapidity until where your detectors go. Here you don't really have that issue, right? Because you plus or minus, so you don't really have much radiation, close to the beam. But if you have PP collisions or EP collisions, you can anyway do it. You can, write down exclusive algorithm that, for example, fixes like 2 jets or 3 jets or 4 jets at the LHC or the EIC, right? That's certainly possible, right? And people have done calculations. So this is one way to do it. The other way to do measurements is to do an inclusive measurement. And what that means is that we basically take all the events where we have a jet, right? And we just count all the jets. So we don't really care about the total sort of event topology. But we just take all the jets. And for example, if we measure the transverse momentum, then we basically, if you have, say, this event with 6 jets, then we just take every jet, we measure its transverse momentum relative to the beam, and then we put it here in the appropriate bin. Okay. So for example, if I have 3 bins for the jet transverse momentum, then say the highest momentum jet in that particular event will count it here. The other one will count here, and the other 3 with slow momentum will count at the slower bit, right? And so I don't really care now, right, if there's like 6 jets in the event, or 5, or just 2, right? I'll just measure whatever jet I find, and I put in an appropriate bit. Okay, and that's of course very different, right? Like I don't throw out any event, I don't enforce any topology on what the global event should look like. I just take all the events. And I take all the jets that I find in any event, right? And that's very similar to the way you do hadron measurements typically, right? If you look at, for example, JLab physics, and you do like CITES experiments, or you do hadron measurements at lab, right? Usually you do these kind of inclusive measurements, right? Where you just take all the hadrons you can find, and you just put them in an appropriate bins, right? And so every event is counted in that sense several times, right? So just depending on how many jets I find, I'll measure all of them. And that, as it turns out, leads to very different theory calculations than this one. Okay. And that's of course also very useful at the LHC, right? Because you don't really have to worry about a lot of radiation going here sort of in the forward direction. All you require is that there is some jet or multiple jets in the event, and I just measure them. I measure their momentum and their substructure. But as it turns out, the theory calculation is quite different. This one is very similar to the way you would measure inclusive hadrons. And so basically you can actually recover the hadron cross-section, right? If you basically, in your jet algorithm, right, we have this parameter R. If I take the limit of R going to 0, then that will just give me an inclusive hadron production, right? Where I would use a fragmentation function, right, to describe that. So in that sense, this is sort of the one that's closely connected to hadron measurements. But of course, they're both relevant, but it's sort of important to have that distinction because in the literature it's discussed in different ways. Okay, does that kind of make sense? Okay, so yeah.
Do people do exclusive measurements also at hadron colliders?
Right. Yeah. So basically, what you do there is you impose a cut on rapidity. All right. That's sort of depending on your detector acceptance, and then you require that in that rapidity interval, you just find say 2 jets, and you require that, or like the way you do it is that the total transfer momentum of all the other radiation that's within that rapidity interval is less than a certain threshold. So in that sense, it's like here you have a cut on the total energy, right, of all the emissions outside the jets. And in PP equations, you would have a constraint on the transverse momentum of all the emissions outside, say, the 2 jets, but in terms of transverse momentum relative to the beam. But it requires 2 things, right? It requires the rapidity cut and a transverse momentum cut. And so that makes it a little more complicated to do, but it's definitely something people have done. And for example, like for some searches of BSM physics, that can be useful because I don't know, some BSM models you require like 1 jet and then, or maybe 3 jets and then nothing else or something like that, or like some missing transverse momentum. So you can sometimes combine it very nicely for certain searches. So yes, it can definitely be done, but it requires very different calculations, and it does not. I'll get back to it a little bit. It does not have this. Right from there, you cannot really take the limit to hadron production. Hadron production, you will always measure, this inclusive way, and like here we can actually take that limit with sort of a very similar analogy, or like as we'll also see, like the theoretical structure that we'll obtain in perturbative QCD is going to be very similar. Any other questions? Yes.
In EP collisions, if let's say in an event it has di-jet production, would that imply that no other type of jets are present? Like there are no 3-jet formation or anything like that?
So it depends how people define it when they say di-jet. It can mean all kinds of things, right? Sometimes people refer to the Haar scattering process, that is like a di-jet event, right? For example, they go to the bright frame, then they require at least 2 jets. But also there, I believe at Hera, people measure, for example, the 2-jet rate, the 3-jet rate, things like that can be useful to extract alpha S. Or for example, what they require is, for example, if you do TMD physics, right, then they require like di-jet events where they're back-to-back. And so that is kind of similar to this, right? Where if you have a back-to-back, or also, here, right, what you could measure is basically the imbalance, right, between them. And if your leading order process, right, basically it's like 2 quarks, right? If I have that imbalance to be very small, that's effectively the same as putting a constraint on the additional radiation, right? Because if I had an additional radiation, I would basically get like a 3-star and like a third jet, like a hard third jet, right? Then I'm not in the back-to-back region anymore. So often when people talk about TMDs, that's very similar to exclusive things, but it's not done by sort of measuring the rest of the event, but it's done by just measuring sort of the signal jets and having a requirement on those. So that can also be something when people refer to di-jets that, they sort of indirectly enforce like an exclusive constraint. But again, like then the theory calculation again changes, but that's also what it can be. Yeah, thanks. Okay. So there's different ways to do calculations. The main 2 are to just do numerical calculations of fixed order for jets, and the other one is trying to do analytic calculations. I'll mostly focus on the analytic calculations because that's what allows us to do jet substructure calculations, but at least I want to mention the fixed order calculations as well. So if we want to think about proton-proton scattering to jets, then maybe I missed the leading order diagram, but so I have basically 2 protons coming in. I'll produce, say, an inclusive jet, right? Then at leading order, I would consider, for example, a diagram that looks like this without this virtual correction, because or the one loop. Right, so I would have basically proton scattering, 2-to-2 scattering processes. And I have that, this is say the example for gluons, but of course I have that for quarks and all kinds of mixtures between quarks and gluons. And I basically, that one already will give me an overall, if you square that thing, right, then you will get an overall alpha S squared for the leading order process. The leading order process for this is specifically for reclusive jet production. That has been known, of course, for a long time. And then, doing a perturbative series expansion or power expansion in alpha S, what we then have to do to be more precise is to just go ahead and compute these higher orders of perturbation theory, right? And the more we can compute that, the better it is, of course. And so just to give sort of a sense of, that this, can be very difficult, this one loop calculation here, the NLO, right, where you basically then include these virtual corrections here, you also include, these real emissions, right, that's similar to what we discussed yesterday, 40 plus or minus. That was done here by Ellis, Kunz, and Dave Soper in 1990, so quite some time ago. And then just to go one order higher in this expansion, where you include, for example, diagrams like this, where you have two real emissions in the final state. Right? That's generally then contribution that appears here for the first time. That was done in 2019. So almost 30 years later, right? It took almost 30 years to compute one order higher in that perturbative series expansion. And these people really worked on that. Sorry, it's both of those. They really worked on that for more than 20 years or so. So it's really, these are really long-term efforts, right, to just write computer code that evaluates Feynman diagrams and that does the integrations, and that makes sure that, right, you have a lot of divergences here that we also saw yesterday in the plus or minus calculation. And if you go to just one order higher and you do it in PP, it's really like a several decade long effort to do these calculations. And of course now they're working with N3LO and one order higher. I don't know how long that's going to take. So that's one way of doing calculations, and you can see here comparisons to LHC data, and that's sort of one way to do. So I want to look at a different way to do this. So this one is generally good if you're just interested in total production rates. But if you want to think about jet substructure as well, that often turns out to not be sufficient. And so we'll use a different approach here. And so before I'm going to talk about jets, let me briefly review how we do factorization or QC factorization in general for hadron production. Right? So if you're, for example, interested in proton-proton scattering to hadron plus X, so inclusive, then what we generally need to look at is a diagram that looks like this. Right? And I guess you've seen these kind of factorized approaches. I guess Matt Stewart covered that to some extent, somewhat.
Not much.
Okay, let me say a few words about it. So what we have is two incoming protons, right? So these are non-perturbative objects, and then they basically describe the distribution of partons, of quarks and gluons inside the proton, right? Also, Anton talked about those kind of things yesterday. When he talked about subleading twists and things like that, right? We're not going to do that. This is just leading twists, just regular collinear PDFs here in the initial state. And then we have two partons, they can be quarks or gluons, that they then scatter, and they produce in the final state. So that's the Feynman diagram that I showed in the previous slide, for example. And then in the final state, we have a high energy parton, which eventually turns into hadrons, and that's again a non-perturbative process that is captured by a fragmentation function. And so what that means mathematically, if you want to write down now the cross-section for this process, if we're interested in the cross-section that is shown here, that's kind of the simplest thing we can do. We're differential in the transverse momentum of the hadrons and in terms of their rapidity. So these are the two quantities that we know how energetic they are, and we know the direction relative to the beam axis, right? So then the way we can write down such a cross-section is in terms of these two parton distribution functions, the perturbative hard scattering pieces, and a fragmentation function. Okay. Only this piece here, the perturbative hard function, is something that we can compute in perturbative QCD. That's basically at a high scale, so we can do this perturbative expansion that I talked about a few times. And then these components here, the particle distribution functions and the fragmentation functions, are non-perturbative. So here we cannot use perturbation theory anymore. but they're universal, or ideally they're universal. One has to show that, meaning that if I know them once from certain reference processes, I can use those, I can extract them from data, and then I can use those to make predictions for other processes. So for example, I could use deep inelastic scattering from Hera or JLab, right? And I can extract those PDFs, maybe also the fragmentation function, and then I can use those to make predictions for the LHC, right? That's basically what it means, that we have universality, that I can extract them once and I can use them to make predictions for something else. And you can see here examples of these. These are the partial distribution functions. That's the function of momentum fraction x, and the analogous version for that for the fragmentation function is shown here, which is the fragmentation function of parton I to say of pion, again as a function of the momentum fraction z, where z is the momentum fraction contained in the hadron relative to the initial parton, right? Like this hadron here will contain momentum fraction something between 0 and 1 relative to the initial quark in gluon. And this non-perturbative process, this non-perturbative function, is something you have to extract from data. That's one example here. What it shows, just word about the functional form, because that's going to be relevant. As you can see, it kind of falls off toward larger values in z, right? So what that generally means is that it's very unlikely that I find a hadron that carries all the energy that was initially available, right? It's much more likely that if I start with a gluon, right, it'll sort of split into several hadrons, right? That's why I have a peak sort of in this low momentum fraction region, and it's very unlikely if I find a hadron that carries almost everything that was initially available. Okay? That's sort of a defining feature of hadrons, right? That this fragmentation function goes down for large values of z, so it always falls off very steeply toward 1. And of course, with that factorization, even though I cannot compute these non-perturbative functions perturbatively, what we do know from the perturbative side is how they change in energy. So that's the scale dependence governed by what is called Dieglab evolution equations, where if I want to know the parton distribution function at a different scale, a different energy scale mu, then I have to solve this equation. And it's given here on the right-hand side is given by the PDF or the fragmentation function convolved with some splitting kernel. And then I have like this integral, and so I have to solve this integral differential equation. And by solving this, I can basically measure the PDF, say at JLab energies, and I can evolve it to LHC energies, and that's predicted by perturbative QCD, right? And that's sort of related to universality and things like that. Are there any questions about this sort of starting point of QCD factorization? Of course, this is like an approximation, right? This holds up to terms that are, hopefully power suppressed by something like 1 over PT squared, which, generally for all practical purposes is usually okay, unless, we push to very low energies. You guys have seen that before? Does it make sense? I see some people nodding, but not. Otherwise, like that's kind of sort of the starting point for jet physics as well. So we should make sure that that's understandable. No questions means yes.
The universality of the PDF, how do you the PDF or universal?
Yeah, you'd have to show that that's actually right. You can write down like an operator definition, and if you then look at a different cross section, right, you have to show that you basically get the same quantity. For anything that I'll talk about here, these are just collinear PDFs, right? This universality issues get more relevant if we think about TMD PDFs, for example, where I'm not only, but they're like collinear, meaning here they only depend on this collinear momentum fraction, right? So like the total proton momentum, say 1, right? And then the partons that scatter carry a momentum fraction, in the longitudinal direction, that is somewhere between 0 and 1, right? That's sort of the collinear PDF. If we would have to think about TMD PDFs, where I'm not only interested in sort of the collinear direction, but I'm also interested if there's some small transverse momentum that these partons have inside the proton, Then I have a more differential PDF, right? There's like collinear and I have some transverse perturbative intrinsic transverse motion. Then I have to worry more about these universality effects. For these collinear PDFs, that's usually not so much an issue, but for the other ones, one definitely has to worry, where the universal and sort of has to be much more careful about gauge lengths and stuff like that. Here, it's just collinear. For anything I'll talk about, it's they're going to be universal.
It is a theoretical question.
Right.
You define an observable, you calculate it, and you show that the same operator definition, operators that or matrix elements that enter in GIS also enter in that particular observable or anything else that you might want to write down. In principle, you have to show this for each observable that you analyze. In practice, we have studied more observables than we have proofs for. But everything seems to hang together. So when you try to analyze all these observables in the QCD global fit, it looks like that a universal set of PDFs, hooks and glues, works for all the observables. So for the collinear ones, it's not a big deal. There is only, it's minimally not included, minimal differential. So you're not measuring much. And therefore, there is not much theoretical travel into extracting this matrix elements from your observable. If you go to something more complicated, you measure more variables, you measure more particles, then it becomes a there are counterexamples. There are examples of observables that cannot be factorized.
Right. Any other questions?
We have any questions from Zoom?
No online questions either. Okay. All right. And so, of course, like this is really nothing new, right? Like this stuff was developed in the 80s and 90s. So this has been around for some time. The interesting thing, though, is that kind of structure was not known really for jets. And so that's something more recent. And that's what I would like to talk about. So as I mentioned, in this factorization, right, so I specifically want to focus on the final state, right? Here we had a fragmentation function that tells us about this transition here from parton of quarks and gluons to hadrons, right? We have like non-perturbative transition between them, right? And so the interesting thing is, if we're now interested not in inclusive hadron production, but we're interested in inclusive jet production, then I can write down really the exact same form of the cross section, right? I still have two PDFs. I still have part functions, right? And they're the exact same ones. But what I have now in the final state is, not a transition from partons to hadrons, but I have a transition from partons to a jet. Okay, and that's now covered not by a fragmentation function, but it's captured by a jet function. But it's very similar in the sense that it also depends on some collinear momentum fraction that tells us how much of the initial momentum that was initially available is actually contained in the jet. Right? And that's basically the main question I'm sort of trying to answer, right? Because before we saw that these jets are very good proxies of parton level dynamics, right? And that should mean that hopefully, right, not like the fragmentation function, right, that falls off very steeply toward 1, but for jets, hopefully we actually, get a significant contribution close to 1, right? Meaning that they're very good proxies for parton level kinematics. Versus for hadrons, so they're sort of all spread out and we get multiple hadrons. But here, the hope is that for every jet that we find, for every parton that we produce in a hard scattering event, we also get a jet, right? So the jet function hopefully looks very different than the fragmentation function, okay? And that sort of can give us a theoretical explanation of why we have this, very close correspondence between partons and jets. And I don't know, when should I actually stop? Maybe should we take a break before we? go more into the
No
calculation.
questions and break.
Right. Are there more questions? So I'll talk more about what these jet functions are after the break. They basically then depend on the jet algorithm that we choose. They depend on the jet radius, and they basically capture that transition right between jets. And that's then the way to do a calculation. That's how we can then compare to experimental results. So that's sort of the underlying idea. Yes. Yes, they turn out to have the same. Yes, but one of them, this one is non-perturbative. You have to get it from data. This one is perturbative, so you can just calculate it in perturbation theory. But it turns out they follow the same D-club evolution. So I'll show exactly that on the next slides. Thanks. Anything else?
More questions, please. I know that after a week we got out of habit, but before we were asking so many, it was so nice. So please go ahead. Well, you may realize or not, but speakers and teachers and lecturers also, your professors thrive on questions. At least that's one of the best things that I experience in class. Yeah, well, I'm also dragging my feet so that we can get some coffee there. So, but the drill, okay, fine. Now we will try to get out on the deck to have our coffee break. We will roll our the cart with the food, but you can grab the coffee before getting out. So this is how we will today. Maybe we can also take 20 minutes now so that we have a little bit of time